appreciate robot enthusiasts. Haddington Dynamics actually started forming about 4 years ago because we're all neighbors and we lived in the neighborhood of Haddington in Las Vegas. So that ended up the name. We formally filed for our company in March of this year and then came out of our garage in July. The backgrounds are very diverse. My background was a research chemist for 5 years, then got into sales, and then owned a recruiting firm. Richard Fu, our CEO, is an investment banker. We figured we'll be dealing with them some days. Let's have one of those guys on our team. Gary Coaches, engineer. He's 37 years in EE, ME, CS, applied math, and has 13 patents. And then Kent. Kent is 3 decades in being a pioneer in FPGA computing. And that's what we want to give you some insight on what makes us different. How are we getting some of the things we're getting off of 3D printed parts? And truly, oops, they're back here. We'll give you a foundation, the invention applications, and then we'll go right into Q&A. So highlighting Kent and that this is some sound research behind here. He built his first parallel processor in 1984, and then first widely used FPGA application in laser printing in '88. First 128-track recording studio in 1990. First patent in microprocessor sitting in Xilinx now, fortunately. 1996, first hypercomputer, or what's an FPGA supercomputer, 97. And then for those that don't know, FPGAs have the reputation, and it's justified, that they're extremely difficult to program. You can take teams of 30 engineers to use some of the software programs to program them. So Kent wrote his own. And that kind of allows us to do the secret sauce deep dive into FPGAs and pulling the most out of them.
Wrote your own compiler?
Yeah.
Okay.
Yeah. And then first FPGA 3D printed robot in 2015. We put this up because this is tried and true science. These are some of the people that work with Kent at NASA and the Air Force Research Labs. And then combined, oh, I skipped one. Hello. Sorry about that, guys.
Just read it off your shirt.
Yeah, there you go. Then again, these are some of the past partnerships and collaborations with Harvard, Biomedical, National Cancer Institute. Kent holds the record for the Smith-Waterman equation that you're taking 3.8 billion pairs and matching them up this way along each line. So let's go into hypercomputing or supercomputing. When you use an FPGA, what you get out of it, it's reconfigurable, inherently parallel, high security, we can get into that later, high speed, scalability. So you can deep dive onto it. You can create a real-time physics engine, a real-time kinematics engine, a real-time metrology. You combine those and we get what we call HD True Touch. That's that haptic feedback. That's telling you I can sense you, and that can be sent over scale and distance. Do a quick bio. We shoved all this onto the FPGA. Actually, this isn't drawn to scale because we're only using half the FPGA. There's a whole other half for people that want to start playing with it. Will act as that bus in between. We got our optical encoders, motor amps, and then the software stack we're putting on it. We wanted to make this as easy to use with the science. So it's got a Ubuntu Linux stack on it. So anything you're comfortable programming in, you can drive the robot. That's our goal, is ease and friction-free. We talked about the optical encoders. What are we doing with them? So by sending a sine, cosine curve, interpolating that, and then taking that 2 million measurements a second on the robot is what gives us our precision. That's a lot of data you can run through a lot of different This was our vision. We said we're Jeremy Rifkin fans that the third industrial revolution, tech is fourth, but society-wise, this is new technology, and we want to democratize the means of production. We have 3D printers that they're good at, they're your micro factories. They're still, in my opinion, in the dot matrix era. But when you can do true heterogeneous direct visual manufacturing at home, you can democratize the means. We can also equip the consumer to become the producer, build real haptic relationships, create immersive telepresence, transform people's mindset, accelerate the changes that are coming in communication, transportation, energy, and automation.
So you're just in it for the money, basically.
No.
Money is a means to,
Yeah, we have to plan that right now. But when you know you have some massive parallel computing, then you can have a clean sheet to robotics. So when you're exploiting 276 Gmax, or that equates to 138 gigaflops of supercomputing power embedded on that robot. And then by utilizing current 3D printing technologies, we can make hundreds of iterations off this to fine tune it and optimize it for cost, weight, power. This was actually predicted back in 1968. Ken had a chance to talk to Woody Flowers at MIT, who relayed this directly to him, that Marvin Minsky on the computer science side said someday computers will be fast enough, algorithms will be robust enough, you'll be able to measure out the mechanical errors of the system. And then Dexter is a reconfigurable FPGA technology demonstrator. And Christopher Fry, who I'll talk to later, came and said, no, this sets new standards for robotics when you can program this fast. Someone asked, well, how do you make money? Have a couple beachheads. We're using robotics as our first one. And we did a soft launch at Maker Faire in New York, had a booth and said, don't go after entrenched, go after the makers.
Why didn't you come to Maker Faire San Diego?
Because we burnt out a board, and I had to call Hansel the day before and back out because we had nothing moving.
yeah.
Otherwise, and that's another reason here, out of pure guilt. For missing that.
Oh, well, good then.
We'll get into this. You can crowdsource because this is attached to the web and has the power of the cloud. I'll have a few slides on crowdsourcing the training. There's certainly the social interaction model with a true haptic telepresence. There'll be a little black box on some of the IPA, so we at least can salvage an OEM model and get this in there, and they can design what they need, and then automation. Here's some of the specs. Just wanted to make sure you guys had that. It weighs about 6.5 kilograms. I had 45 watts in, but the man in the back here is just a genius. He retook our control board, Gary. So it's a 6-channel control board. It runs from 7 watts up to 45. Volts. And then got it down so we can run this at 20 watts. So that's powered by a small solar panel. It's got Wi-Fi, 4 USB ports, and then 1 10-bit GPIO. We're getting 50 microns, and it's load independent. It knows it has a load and will get to the right spot. And so that's something a little different as well. We're stepping at 5 microns. You can see the degrees of rotation, and then we're moving about 50 degrees per second. Now, if you don't need the precision, you can speed that up. And this is on path as well as point. So in cost comparison, you got Sawyer, that's 0.1 plus or minus, that's 0.2 millimeters, and we're at 0.5. But cost-wise, you can buy a lot more of ours. So instead of buying one, buy 7. And if you got a kit and want to build it on a kit, our pricing allows you to build a lot more. We put this slide up there because with HDIQ, and then just depending on the applications you want, we can touch every industry. And there's a slide on that we'll get to too, from agriculture, medical, military, nano, microassembly. That's where I'm excited about. right on down to the scale. And our goal is to, as these start building themselves, being able to get the cost in play and getting these hopefully with Hansel's help into other kids. Big data learning. When you train one robot and more people train that robot, and you know you got a lot of robots with the training, that can go and be mined. And then that jumps down and you can shoot out best practices for your robot, or if you need your robot to train a human, now you got a hyper expert. Going to crowdsourcing robots, you can start learning reason, control, planners, creative solutions. That's bi-directional. Cloud robots, robots can leverage a cloud. The one thing we're different here is we don't need to free up the robot from computing constraints on it. We don't have that, so we can use a cloud for what it is. Dial in Watson on this, and you got a very aggressive pepper. So that's the things we want. By having the Wi-Fi, by having that supercomputing power, we can supercomputer in the robot and supercomputer in the cloud. We're also working with Dr. Stephen Thaler. He's 25 years hierarchical convolutional neural networks, vision systems we can put on here. And his is the creativity engine. Since the soft launch, this is, again, we sold out our inventory. We wanted some inventory there. We sold that out. But the people that approached us to say, hey, we want a solution for what you're doing. If there's a price point that's been met, can you work with us? And so the clothing manufacturing is interesting because if you can figure out how to pull cloth and move cloth or pick something up with a certain force and cut it, that's where we think when you solve that, other stuff's easy. So the other one we wanted to, Christopher Fari, we met him at New York Maker Fair. He jumped on this project, so his own time, he's got about 350 plus hours into it, writing a 5th generation language program. His view is write it at all levels. Don't do low level, do high level. Scratch was one of the programs that he said it does things very good, but when complexity gets very, very tough, I don't want some of the constraints, so I'm starting it from scratch. Literally. Dun, dun, dun. If you want to see it, this is what. Oh, I'm not on your Wi-Fi. Never mind.
You might be.
Yeah, I'm on yours actually.
Yeah.
So we got.
You got 2 of them up.
Yeah, 3 of them.
Yep.
So as we can go through, don't need to go through this now, but this is being worked on. That whatever language you want to pipe in here, that you're comfortable writing with, shoots it down, makes commands for your in our Dexlex, and then you can simulate it. Phase plan, and this is why we want to share this with you only because if we get more people that are interested, and there's a sweet spot in here. Open source release, the geometry, so is what we'll release so far. So 3D printers and want to start printing this yourself, and then buy the boards later. Great. Inverse kinematics, that's the one thing we're working on. We have a working solution for that. That will go on there, and that will allow that real fine. Our goal is fractal 3D printing. End effectors are having that universal attachment, so you can start, if you want to develop your own grip or develop your own tools, you can then pipe that back into the robot.
So how would we get the electronics if we were going to print one of these ourselves?
Yeah, we'll send them to you.
We'll send it to you.
Yeah, that's part of the business model. I mean, we're open sourcing the electronics also, but until but we'll sell them. We'll sell you whatever we got.
Wow.
But
Phase 2, same stuff. As we keep pushing this forward and expand its capabilities, and we're hoping other people expand it again. That's why we want to be open source. Wherever we get creative, we will certainly help and reinforce. Breakdown. So to get into some of the 3D printing, we 3D printing, but with the Z-axis, there's going to be that weakness. So we had the reinforcements. So there's slots and holes to add the reinforcements that you can keep that machine rigid and get rid of the Z-axis issue. A couple other ones, there's a base. And so what we're showing here when we're dissolving is the carbon fiber strakes and then the hardware we're adding. So the geometry will be also released, I think, in SolidWorks. Is that right, Gary? So
yeah, just step files and
step
STLs.
files and STLs. Every component on this robot was designed specifically for this. Is if it can build itself or many build faster, you lower your costs and get these into more people's hands. I think that's it. I wanted to get into some of the, Ken can go into.
When you say build itself, does that include assembly?
Yeah, well, that's the idea. It's the rep wrap model, squared. Right? So, things
It's
with
not just the parts. But
yeah. So fabricate the parts and assemble them.
Well, obviously not the steel or carbon fiber.
Not the steel.
parts,
Well,
but-
actually, the carbon fiber. So we're actually one of the heads that we're building is a carbon fiber layup. You know, head, like have you seen the X winder? Seen the X winder? Yeah, it's basically a mandrel winder for carbon fiber. That's and also the same algorithms that you use to do mandrel winding. You can wind your own stepper motors with too. You might wind your own motors.
Yes.
Build your own stuff.
To 3D print it.
Well,
What did we
can't make
use?
the
We
magnets,
used
but almost everything else.
Why did you choose to do it?
Why do we
Yeah.
choose to do it?
Well,
For ease of
got plans
manufacturing.
to do it.
When you can print out different parts and make sure you get the mechanics right, you want to do faster iterations, and it just sped up our production model. Plus, it was a great way to say if we're getting sub 50 microns on 3D printed parts, it's telling people that's a little different.
Yeah, that's actually a really good
Really
question.
good question.
Yeah, one of the reasons for doing 3D printing also is that we knew that we can put an extruder on here, and so we could turn this into a 3D printer so that it could actually fabricate its own parts. So that you can actually use this as a large format external envelope 3D printer. So that's
Really good.
Yeah.
And then the printers we used, we started with the MakerBot that Ken had, and we ended up burning that out, and then bought some flash forges to get the rest of the parts done.
So, no, go ahead.
I was just going to ask, are you planning on commercializing your FPGA programming tools? Just out of curiosity.
You know what? When I did that supercomputer company or hypercomputer company, we tried to do that, and it's a really different kind of language. Some people call it Lisp for hardware, or graphical Lisp for hardware. It uses a lot of formal logic constructs and stuff, and it was very difficult to get people to learn.
I threw it
how
out
to
there
use it.
just so you say.
So the learning
We
curve
want
is
to
just-
we
The learning curve is
want
just
to
brutal.
eliminate this for
Well,
you and
it's
just
actually-
tell us what algorithms you'd want run on it, and we just create that interface.
Yeah. So it's basically it's a generator of generators.
Right.
And so we're going to provide an interface where you can like type in formulas and stuff like that. It'll send that to the compiler and actually generate the code and put a DMA engine on each end of it so that you can actually access it through Linux. And so to make it really simple to kind of create computational pipelines that you can tap into. And we actually have a whole library of all the vision stuff with full Gaussian hierarchy builders and the Fourier time frequency domain and registration and multidimensional correlation and the full basic linear algebra subroutine. So those are all are available as parametric pipelines. So depending on if you want complex numbers or different precision, you get the 77-bit fixed point. Then you just parameterize that and regenerate those. And
You heard a company called Obreri? They're doing a lot of work with 3D printing and laser cutters and things like that, but that's not their actual focus. The focus is on building a system that's very complex like that, but that has a very simple user interface that takes very general design guideline and then adds all the manufacturing
parameters to it.
knowledge
Yeah.
into it automatically. It sounds like it's kind of
Well,
the
that's
same
what
thing as
Fry's
you're
doing
trying to
at
do.
MIT Media Labs. I mean, he's a language expert, and that's his whole thing. Is like, how do you translate human language into machines, machine type of language.
But also adding in like the knowledge of the people who really understand the system, so that it doesn't allow the end user to do something that's impossible or stupid
all the
or
constraint
all the
management.
constraints and all that kind of stuff.
You got another question?
Yeah. Does your robot have any other use other than copying itself? And also, if somebody bought one of the copies, wouldn't they just make more and more and like improve the design?
Hopefully,
Yeah.
absolutely,
Yeah.
yeah. But you can also use it as a game controller, where you can actually sword fight with someone and actually feel the swords crashing together. So there's so
Yeah,
Uses
wherever
are endless.
robots are used
Yeah.
right now, and if they need them cheaper and precision, that's a commercial use for ours. A big picture, what we would love to see is going back to think of the replicator on Star Trek. That tech has to start somewhere. And so if you say, I need to build this, and it can build this, or you have a whole internet of things to choose, I want to build this, and it can dump right in that, and you just add raw materials and print and build what you need when you need it.
it's your own personal factory to build anything you want.
So has anybody looked into the legal challenges? I'm thinking about the rep-rap movement.
Oh yeah,
There was a lot of legal
yeah.
issues.
Well, that's one of the reasons we're selling them as kits, right? So.
Ah,
And we'll sell you 3 different versions of kits, including the final version being you put 3 parts together and plug in the wiring harness. So it's it's not a final product. We're basically offsetting it's the old Hayes modem patent workaround, or not patent, but liability workaround.
right.
So
What about scalability? Have you thought
actually,
about?
it's parametric. So all the 3D models are all parametric. So you can just dial it up or dial it down, and it'll print them at different sizes.
When the parametric models, what were they actually made in?
Inventor, AutoCAD Inventor.
AutoCAD.
So you've been emphasizing FPGA versus, I assume, like a general purpose microprocessor. And
Well, it's a hybrid. I mean, so there's 2 ARM9s on there also inside of the FPGA. That's running the Ubuntu stack, but it's really kind of a hybrid where you've got FPGAs right down, controlling the high-speed stuff next to the bare metal stuff, and then you've got the driver and the Ubuntu stack, and then the wireless that actually plugs into the net, plug into your big analytics and stuff.
So is there any downside to FPGA?
The big downside is just the extreme difficulty of programming. You basically have to have an entire ASIC team, which is 5 people on your time enclosure, and you got your HDL programmers and your architects, and
That's actually one of my biggest complaints right now, is that we're teaching kids how to write programs all over the place, and we're teaching kids how to make things, how to run a 3D printer or whatever. Nobody is teaching digital logic to kids, and it's not that hard to teach to kids. I built a site to try to do that, and it gets donut interest on the net.
Yeah.
So before you start learning anything about digital logic, you're in college, and by that point, frankly, it's too late for you to become the next great designer of a CPU or whatever. It's a screaming loss.
You have a question?
Yeah. So how do you keep the cost low? Because you can pay $3,000 for a single FPGA.
Well, that's the new pricing model for the FPGA vendors is they want to get into this whole systems on a chip, and so they knew they had to price it lower, and the pricing is artificially high on FPGA.
Because there's only 2.
There's a duopoly between them, and
Right,
a good friend of mine Steve Trimberger is
Altera.
a friend of mine
Altera.
at Xilinx, and he revealed to me, he says, "Ken, it costs us more to package those chips than it does to build to yield the silicon, because if you look at them, they're homogeneous. They're like memories. They yield like memories."
Right.
So yeah, the cost is going down.
Yeah. So this is a $50 chip.
So are you specifically using system on a chip type chips because the cost is lower?
Well, because they're integrated, because it gives us the entire stack. So we've got the whole. Yeah.
Because what you're saying is true. It's like
Yes.
you can buy just an FPGA and pay way more
Yeah,
for
pay
what you would pay for the
$25,000
same
for it.
exact capability
Yeah.
in a system on a chip.
Yep.
Yeah.
But would it be as fast?
Oh yeah, yeah. I mean, they're
Yeah,
the
they're
same
the same.
capability.
Yeah, they just price them different.
I was
You have
looking
another
at
question?
Cypress.
Like, is this robot going to print another robot programmed, or do you have to program it yourself?
The programming the robot, actually because it's touch sensitive, the way you program it. The way you program it is you just move it around. So go to this point, collect this point, move here. You can collect points, or you can collect paths, and then just say replay that. So that's really the lion's share of how you program, or primarily how you program the robot, is just by moving it around. That's why we
Can
call
you
it
demonstrate
Dexter.
that?
I can demonstrate that. I'll just do
Yeah,
that.
we can.
Will
You
it
guys,
sort of optimize, because humans are our hands are shaky.
Yep.
So will that
Yeah.
filter out?
Well, that's part of it. So there's
Well, you're doing
there's
waypoints,
gathering.
right?
Yeah, I'm doing waypoints right now. But now I'll do a path. So that's a path. Hopefully this works for me. Sort of.
I jacked the end
Yeah.
on the way in. So.
Let's see. So let's just go. To,
Can I ask you a quick question?
Yeah.
What do you do with the forward USB port hub part?
Well, because you have that Ubuntu, so if you want to plug and drag it,
Oops.
well, because if you wanted to plug in a phone,
The keyboard might be better. Use that point, that point, and then the tab.
The keyboard stuck to the arm.
That's
But yeah,
just
after you capture the paths, and part of this this Dexter development environment that Fry is working on out at MIT Media Lab is it's a path and goal oriented programming thing. So you can capture the paths and then bring them in, graphically say, okay, this was not exactly what I wanted. I want to quantize that to exactly this point and this point, or when I get to the end of this path and I've got an objective that I need to do, which is look at the camera and find a fiducial, adjust the path and then move on to the next path. So yeah, it gives us an opportunity to create a whole new programming model for robots.
it's basically you're one-upping Dexter.
Baxter, because this is
Baxter. Sorry,
Yeah,
you're
that's
Dexter.
a bad
Baxter.
name. I can tell already. It's,
Yeah.
it's either a serial killer or confused with
or
Rita.
mistaken with the yeah.
Somebody actually made that comment too about it being a serial
I
killer
saw
on
that.
a meetup.
Yeah.
Pretty hilarious. So what stepper motor drivers are you using, just out of curiosity?
We're using the Allegro drivers, the
The A something or other?
the 779s or whatever. Yeah,
Because those are just little NEMA 17s.
they are.
You need
Why
much
do
stepper
you-
motor drivers for bigger motors.
Why do you cross the?
On the Kevlar right here, why do we cross these here? I'm just trying to minimize the footprint, and that's another one of the design parameters that you want to do with the robot. Is you want to keep its size small so that it doesn't interfere with the build envelope. And so it was just an exercise in how do we minimize this. Otherwise, we'd have to come out here and we'd have a kind of a longer path through here. So I'm just trying to minimize
You saved
every
it.
millimeter I
You
can.
saved a half an inch.
Yeah.
So those are two separate. I mean, one.
Yeah, these drive the
push-pull.
differential, right? And it's just a single piece of Kevlar wrapped in there for this one, and then a single piece for this
The
one. and then a
differential
single-
in the wrist.
Yeah, these go up. This go up here and drive pulleys here, which come up here and drive
I
this.
see.
So we want to keep all the weight down here so that we can counterbalance everything. So it's actually pretty much statically balanced.
And we just did the bands up here. Those are Kevlar bands. On the other one,
Yeah, this one here's got this kind of
Kevlar,
Kevlar
correct.
all the way up through to the
Okay.
differential.
So with the rep wraps, one of the problems that they have with belts is that the belts will vibrate and you get interesting, strange effects. Did you run into any of that and have to compensate for it?
You
or
know
is-
what? Well, we could compensate. We could actually see that as a sine wave
Right.
in our metrology system. But we use Kevlar and crank it down so that it's super tight.
So there's a method of once you install the motor, you're doing something to really stretch it.
Actually, we after the motor's installed, then we wrap the Kevlar, and it's every.
Oh, it's the Kevlar itself is being stretched.
Yeah. Well, and Kevlar is zero stretch, right? So it's actually we're pre-stressing. You know, the springiness of it is in the carbon fiber and the plastic and
In the mounts.
in the mounts and the shafts that go through here. These hollow shafts. They're actually two different pieces of carbon fiber tubes, and so there's a little bit of springiness in there too.
It's funny because they don't feel very strong from the side.
Yeah, yeah, but that's
But this way is the way they're strong.
yeah, that's there's a technique we figured out to actually it's like a guitar string to tighten it up. We don't have it on this model here, but yeah, you're supposed to tighten it to about an A.
Okay.
So it rings like an A. And that's a 60-pound test carbon fiber. So you're looking at about 600 pounds of force that you can tighten that down with.
So is that one of the most expensive components on the arm?
That's about 20 cents worth of Kevlar.
Really?
Yeah, Kevlar thread's not really. I mean, it's
I haven't
expensive when you
priced it.
build a vest out of it, but just 50 meters of it is, or 50 feet of it is pretty
Just
cheap.
the carbon fiber tubes are the more expensive item?
And the strakes and
Yeah,
the
the
tubes are
carbon
probably
fiber there's about $100 in carbon fiber on that, but that'll come down to about 25 when we start
Making it
actually
yourself.
making it ourselves. Yeah.
And then what else is expensive?
the
Bearings?
harmonic drives.
Yeah, the harmonic drives are kind of the big that and the electronics. So we've got
But we can buy the crap ones, the ones that are.
yeah, we're getting
precise.
these from China that,
So you
that
could-
no one else wants.
Because the slop in it doesn't matter.
Yeah, we just use it for the gear ratio.
Right.
In fact, we have a 3D printed cycloidal drive that might be an easier workaround.
So there's-
even cheaper.
A harmonic drive
3 of them.
Yeah.
here, here, and here.
Nope. Here, and here. So there's a motor and drive built inside of here, and you can see it.
Oh, I see. I got it now. So that one is controlling this joint. This is
Yeah.
the motor for it down
Yeah,
here.
correct.
And then there's one to move the arm this way and another one on the base.
And then the other two drive the differential up at the top.
So did you try making your own harmonic drive?
I did, yeah, and it worked great. Actually, we got a video of it, an early prototype.
I know 2 different people who have tried to make harmonic drives and failed miserably, so good on you.
Yeah, well, it's because you can't make them precise. I mean, the thing about harmonic drives is it's a tool and die process, right? You actually have to grind them together. They're matched sets in order to get the precision out of them.
So you don't just make them, you make them and then you make them to each other.
Yeah. So after you mill them, you actually have to go through a grinding process, like seating a valve seat, in order to make them get the kind of precision out of them. The one that we built, the one critical part that we did, but it fails all the time, is a 3D printed flex spline. Okay, so we actually used a fruit cup, a stainless steel fruit cup, as the flex spline, and then wrapped a timing belt around the outside of it as the gear, and then 3D printed the stator gear, and then the wave generator is just a 3D printed post with 2 roller skate bearings on it, and that's with the metrology and the optical encoding stuff. That was enough to get. Oh, we should show that video.
Yeah, that's fine. We can talk over it.
Yeah.
No, actually, you must have shut down your Wi-Fi. Because I'm not on it right now.
You're on
I am?
go to the logo.
Dexlink. Go Dexlink. There you go. Okay.
I'm actually having trouble with my Wi-Fi too, so I'm
Oh,
gonna
it
reset
could
it.
be.
So when you say it has a 1 kilogram that it can lift out and it's extended, is that before it tips over or before, or is that what the gears can do?
It's the when the stepper motors fail to.
So do you have a load cell or anything in the end? Or
Actually, there's with this metrology system. So we've got optical encoders at all the axes here, right? And stepper motors here. We call it a stepper servo idea.
Yeah.
And so the difference in where you tell it to go with the stepper motor and where it actually is the force that's on that axis. And so you get this integrated force torque sensor. as kind of an emergent behavior, being able to measure it. Well, we're measuring about 160 nanometers. Is a LSB of the analog to digital converters.
Well, and increasing the strength, I mean, you were saying that's the stepper motors, but it should be easy to put in bigger stepper motors,
Absolutely,
larger
yep.
drivers.
Yep.
So then the gearing you were saying is another limiting factor, that it can only handle a certain amount of
Well,
weight.
that's untested. That's
Oh.
that's my first approximation.
That's your concern.
That's my concern.
Yeah, okay.
Yeah.
Nice motion. So do you have some canned motion demos that you're going to spring on us here in a bit?
I did.
Oh,
Yeah. No, it.
Wait,
when you torqued it on the way in?
Well,
you
it was
don't
actually
grab it at the end effector and
it was
move it. Well,
actually the bigger problem happened at Robo Universe. These
these were the
wires-
circles he's talking about on the program.
Yeah.
Is when you can generate that, switching high res. So he's touching it right now, and then we can see that pattern.
So what are those lines again? What are
Well,
those?
that's that's the Lasiduous pattern.
Yeah.
But they're 12-bit codecs, and that's a 512 element
Here's
display
the
window,
3D
so I can
printed
zoom
wave.
in on it, and it wraps
okay.
around. So
I got it. I
that's
got it.
zooming into the surface.
So there's your.
Yeah, that's the 3D.
So you decided to buy those from China just because you didn't have the time to make a bunch of these, or?
Well, that's a good question. The problem is that I used a fruit cup,
Okay.
and in order to get the fruit cup, I had to grind off the lip and all that. And we really want to actually do a custom, either a turned plate or just create a die so we can actually create our own cups with the right geometries. And that's like $5,000 to actually build that die. So it was like, let's get harmonic drives and just worry about that later.
Okay. Sorry, I was just watching it calibrate its base there.
Yeah.
The differences between the different Lissajou figures, is that... Okay, so is that showing the position, or is that showing the variation in the encoder? Over on the part that's on your shirt right now.
Right.
Oh, after this.
That's after this.
Sorry.
Yeah. You see.
I'm sorry, I'm just having a little bit of a difficult time understanding what those Lissajous are coming from.
Oh, yeah.
What they are.
Okay.
It's coming up. It's right after
It's
that.
right after that, yeah.
I'll pause when we get there.
Cross-coloring use of calibration tables. So are you talking then about the variations in the 3D printed encoder?
I am. Yep.
Okay.
Okay. So the base is moving around here, the code disk here, and this is showing what's actually coming off of it, sine cosine. So x is cosine and the y is sine. So
And if everything were perfect, that would basically be a
that's
circle?
a circle, right?
Right.
Yeah. But since they're not, and that each slit in the 3D printed code disk
Little-
is different, so
yeah.
you've got a different amplitude for each one of those, and you get this,
So now you know where you are out of 360 degrees by which one of those shapes it traces as it goes through a single movement.
Well, what happens is we're actually taking and recording this whole thing. So when
Right.
we calibrate, we actually use the stepper motors to move this around at a constant rate. And then we record this and build a table out of it. So then when we turn it around and turn it on,
Yeah.
we're measuring what's coming out of the code disk and looking at the table and say, oh, that means it's that point right there.
Right.
But in order to find the absolute position, we actually run a convolution kernel on top of this to say, oh, which slit are we currently at? And then the amplitude of the sine and the cosine at that point is the decimal position in there.
So what are you going to do when 3D printers get good enough that there aren't any variations? of it?
Actually, it's
Just kidding.
yeah.
Then you introduce
No.
the error that you want.
Yeah.
Yeah.
Well, then what we'll do is when they're that good, we'll purposefully change the
Yes.
phase of of those curves and be able
Putting
to
in
read
the
it
error-
directly off of
Putting
it.
in
so
the error
the
that you
phase
want.
change. Yeah.
Yes, exactly.
Say you wanted to do this, and I don't mean to make the pun too badly, but say you wanted to make this ambidextrous.
Yeah, with two.
Yeah.
Ambidextrous.
Yeah,
Yeah,
I
right.
love it.
Oh, good.
And make essentially the mirror image of this So it could be essentially arms on a mobile platform, i.e.
That's what we're
robot
doing.
or something.
Yep.
You're doing that.
Yep.
So you can actually make a mirror image of your design so it would be symmetrical.
Well, we just
Oh,
rotate 180
you not?
degrees out of.
So you don't
Flip
need
it.
to.
Yeah.
Okay.
Yep.
You have enough degree of,
And the bottom
of
is
movement
infinite.
freedom to.
Yeah, the bottom one is infinite.
There's no
a
constraints
slip
on the elbows and wrists and so forth. If you just
ring. Yeah, it's. I mean,
360.
yeah. It's 360 on. It's actually probably 780 on the pivot. It's infinite on the base.
Uh-huh.
And the only thing that keeps this from being, kind of 780 is, this comes down here and hits this. So this goes all the way down to here and all the way back down to it. So it's 340 degrees on that one.
So why don't you just make it a little bit longer?
You can. And we're actually doing that. One of the guys we ran into, Giovanni at Maker Faire, wants us to build one about 3 times that size. And the neat thing about it is we can actually keep the geometry, the parts all the same, and just change the length of these carbon fiber tubes that connect the pieces together. And that gives us a bigger robot. In order to keep it statically balanced, we'd have to add weight down here. But
So with the speed that you're updating the position at, are you having any issues with crosstalk between the signal wires or electrical noise or anything like that?
yes.
Because it strikes me that you're running really fast.
Yeah, well, it's only 2 megahertz, right?
Well-
I mean, but for a supercomputer, for an FPGA,
That's nothing.
that's like 100 times slower than it can run.
Right. Right.
And actually,
Some of that's going through wires, and then you have antennas.
Yeah,
and
so
then-
we've got it's twisted pair in there, and then we've got there's a differential receiver on the analog to digital converter. So we're getting the CMMR common mode rejection down there at where to go in. So. And that's why there's shielding on the cables.
That's what I was thinking.
Yeah.
That's what prompted me to ask that question.
Now would that
And
be?
actually, that's a really good question because our precision is limited by our signal to noise ratio on those analog to digital converters, and we've got 12 bits right now. We actually have another sensor system that's actually digital. We put the codecs right up in here, and they're 18-bit codecs that run at 30 megahertz. And so we should be able to get into the angstrom.
No, wait. These are the ADD converters that are reading the optical sensors,
Correct.
the
Yep.
phototransistors or whatever.
Yep.
So isn't that? I mean, I understand that you're reading the sine and cosine off of it, and that you're getting a smooth waveform. But in the end, isn't that pretty much? Oh no, you're watching the edge come across the light, aren't you? So you're watching that slowly shut down. It's an analog process.
That's right. It's almost like a diffraction pattern that's coming off of that.
Oh wow, that hadn't clicked yet. Okay. So now I see why that's the limit of your resolution.
Yep. And so by putting the analog to digital converters right at where the phototransistors are, we can eliminate all the other modify our signal to noise ratio and get them away from the motors and.
All that kind of stuff. So then, what are you using, like chi2c, to send it back to the FPGA?
No,
or?
right now,
Yeah.
right now it's analog going through twisted pair analog. Yeah, we've got,
Okay.
Yeah, it's all twisted pair going into the FPGA. The
But
FPGA has differential inputs on them.
But you said you moved the ADD converters closer to the.
Closer to there, yep. And then it turns out that the same pins that are on the FPGA that hook up to the analog are also your high-speed digital I/O. So it's twisted pair the
Just depending on how it's configured.
yeah, and you can actually run a gigabit a second over those.
So that removes that whole
Yep.
issue.
Yep. And get you 18 bits resolution then the dynamic range of the phototransistors becomes your limiting factor.
Right.
Your instantaneous.
So you'd almost have to calibrate that out somehow.
Well, it's just that we could use photo Darlingtons, to get 60, 70 dB of dynamic range in the phototransistor, but we're usually using regular nickel phototransistors on there that have about a 30, 35 dB dynamic range on them.
Should you go to pin photodiodes
Yep.
to get higher speed
Yep.
out of those?
Yeah, absolutely.
Or maybe just use two, have a kind of a vernier arrangement.
Yeah. That's the photo Darlington types. Yeah.
Well, no, I
about
meant
two separate.
Two separate,
So four for
four
the sine
sensors
cosine.
total, and the idea then would be to have two of them here and then two of them a half of a thing off, so that each one would be in the middle of its dynamic
Yeah,
range,
sure
and the other
could.
one was off.
And I did some experiments with that when I was doing laser cut, where you actually have one disc on the outside and one disc on the inside, and you see
Right.
the force that's there.
Right.
Yeah, so I mean, we can basically get. I mean, so the measurement system limits the the precision of this, but we can go down down into the small angstroms.
Well, I mentioned single-track gray codes, and you said that so you can get absolute position. But there's another advantage to single-track gray codes, and that is that you can, because you're using a vernier arrangement of sensors,
Mhm.
you can get a higher resolution than what the mechanical resolution you have to print is.
Mhm.
Because when one is being occluded, then another one is occluded, so it's a vernier. Hopefully I'm making sense. It's easier to visualize that than it is to explain it verbally.
Yeah.
So you can print a disk, an encoder disk, at a lower resolution than you have to with a quadrature encoder, and still get the same resolution.
That's interesting.
Yeah.
Yeah.
I've been pushing single track gray codes for about 3 years now. Nobody listens.
I will have to talk. I'm not quite following you, but
Okay.
yeah, show me a picture.
I got a website. I'll show
Okay.
you later.
How shielded are the detectors on your encoders from ambient extreme
Actually,
bright light
that's
sources?
a really good question
Uh-huh.
because we've got an old lamp back at the office
Uh-huh.
that has that's a incandescent lamp, and
Uh-huh.
it generates a lot of infrared. And
Okay.
we were debugging one day, and I was like, "What the heck? It's not moving. There's sine waves
And you
going
stood
on
in front
inside
of
of
it and it
there."
started
It's
working.
like, "Oh wait, there, yeah, that's the lamp."
So could you go to
So-
some kind of like a magnetic
Okay,
pickup
so we're-
to-
yeah, so
for
the-
environments where
yeah,
you
the-
have
No,
maybe-
you're gonna put
Yeah,
a
we just covered
shroud
up.
on it.
Yeah, these here are we'll just cover them up.
It works great until you take the cover off.
Yeah.
Then it goes
And
crazy.
you have an incandescent bulb somewhere.
Right.
just don't get it close to a heat.
Or take it
Right.
outside.
Well, and the photo transistors and diodes we're using, they're narrow band too, so they're like 915 nanometer. And if you look at the
The
Which is-
response on
which
those
is-
guys, unless it's got a filter in front of it, it's pretty broad.
Yeah.
It's not.
it's
too
not,
narrow.
it's not
You could put an interference filter in front of that if you really wanted to narrow it down from any extraneous adjacent.
is that just an optical?
It's an optical, yeah, not with a very narrow bandwidth, so like maybe 3 nanometers or
Oh,
1
wow.
nanometer or something. You can really, and then instead of using LED, use a laser, right? So that would narrow your wavelength. You can put interference filters in front of that. And then
Well, then you could do true infrared with it too.
You could.
Laser.
yeah, it'd be coherent. So yes, you could.
So I noticed that there's USB ports on the ARM
Yeah.
itself. Now those would be for like peripherals that you're
That
putting
plugs
on.
right into the Ubuntu stack there. So yeah.
Right. But what's the use case for that? Is you're putting something on the end effector here
There's
that then
actually,
you plug in?
yeah, we put USB all the way up to the end effector too, but
Oh.
we've got USB on this outside. So, well, we're putting it on a mobile platform, right? So you can put a cell modem on there and accelerometers or a
That's why I
you know,
wanted to see
GPS
ambidextrous
system.
on legs.
Oh, you want it on legs?
Yes.
Actually, yeah, probably.
Go win that next DARPA challenge.
Oh yeah, the walking
Yeah.
robot. Actually, you could. This would be an
That's what I was-
ideal platform.
well, that's
because
what I
you
was
could actually
thinking,
run
yeah.
the balance algorithms in real time too,
Uh-huh.
and do it in direct form without having to do things
And
like Kalman filters.
You've
and
got
stuff like
arms.
that
You
on
could extend this whole concept to legs.
it. Yep,
Yeah.
absolutely.
Just flip them upside down.
Yep.
Put in a little bit
Right.
bigger motors.
So the bigger
motors,
motors
yeah.
upside down and
Yep.
tweak your algorithms and you've
Or
got
just put in better harmonic drives.
Yeah. Higher doing 201 or something.
He worked with Dr. O
Oh,
and UNLV.
oh, cool.
Actually, before he was at UNLV.
What's that? Oh, you
Before
were
he-
before he moved to. Okay, yeah, he's one we want to meet. Some good people.
Yeah, because there's all kinds of more advanced dynamic control algorithms, like noise cancellation and echo cancellation, stuff like that to control the. Because right now we're running basically staggered state PID controllers, but we can do the gain scheduling and stuff like that relative to the acceleration. But we really want to be able to do model the entire thing with like a 10-element finite element analysis, so that we can use that information and drive that into the control loop, so that we can stop create path accuracy throughout that high speeds through it too. So we've got the measurement speed and the computation to do it. We just have to do those.
Another question here.
Approximately, when do you think you will be able to finish this?
That is a really good question, because I'm a tinkerer and I never finish anything. No, that's what we're here for you. You guys have to finish this. That's what another reason we're open sourcing it. But we are releasing this version, and we're shipping the first units in March, April. So we've got
You've got a deadline to meet.
we do, but we have the parts to build 120 robots, and so we'll be able to make that deadline.
So did you seriously 3D print parts for 120 different robots, or did you have them cast?
We are printing right now as we speak. We've got a little 3D
Little
print,
forge factory.
So we're burning out the 3D printers
Yeah,
almost every 6 weeks.
yeah.
we like their warranty.
So one of the things I've run into myself in playing around with 3D printers is it takes bloody forever or something to print, and then I want to make a bunch of that. So I started off by trying to 3D print a mold, and then casting plastic into that. Unfortunately, the plastics that I wanted to use bonded to the mold, so I ended up printing the positive part, making a silicon mold, and then casting plastic. As a matter of fact,
that's one of the things that we do, and actually that's one of the techniques we're going to get used to do the differential gears up there.
That's interesting. So, and hopefully the casting is precise enough.
Yeah.
Not that it has to be like a regular gear train precise,
No,
because you can compensate. But.
Yeah. Well. Yeah. We haven't done that yet. So,
Haven't tried.
So
Okay.
that's a good.
So I was asking about the USB connectors because you were talking about the base being infinite.
Yep.
So Wi-Fi, obviously, then you can communicate with the arm very nicely that way. Do you have USB going through the slip rings, or
No, it's just power.
Just power.
Just power.
So
we would put another one of the control board on the main platform and talk Wi-Fi to it.
exactly. Okay. So now you've got a kind of a bottleneck there. Not much of one, but a little bit of a bottleneck in terms of how much data you can move back and forth.
Yeah, but it'll have its own FPGA on it too.
Yeah, for its own things.
Yeah.
Exactly. But getting the data back and forth. So I was thinking about the walking robot. The big issue there is that you have to solve the whole system really, really, really quick.
Yep.
So, well, obviously, you probably wouldn't use the slip rings for that system. You would need to. Yeah, you would need to.
Well, we could. There's I've done data over power before, and I've looked at that. And we can easily put another couple of channels on the slip ring too if we need to.
Maybe some
going
error detect and correct. And
I'm not going wireless, I'm
Yeah.
going fiber.
Or going LED
to sensor, yeah.
Yep.
Okay.
Have it in the center and just have the two of them there so they can talk light between it. Yeah, that's something to look at too.
That
Also,
was fun to
capacity
work on.
coupling between so you can actually Well, you put a trellis code on there and to get your it's actually I've done a lot of digital radio with that, so you can get hundreds of megabits a second out of a capacity coupled connection.
It's cool. Okay. Just out of curiosity, have you ever worked with passing data through meat in and out of the human body, in other words? Or out of body? No?
Pass me through my body.
No. I have a client who's trying to do RF in and out of the cow.
Oh, really?
You mentioned that about data.
You mean through the cow or in and out of the cow?
Well,
Like
from the cow's stomach to outside.
internally,
of
so
the
like
cow.
swallow a pill or something for some kind of reason.
It's a data logger.
Oh, it can be, well, depending on the frequency that you use, it might not be a big problem.
It is. Or it has been, put it that way.
You
So one of the things we're doing.
cook your meat would be good. You could use it like frequency to get attenuated, but if you go to
Cut down on the
So-
preservatives, right?
say you could use something even up to like 20 megahertz or something, that would probably go through free.
Any other questions? I know we got about Ansel, this is a 715 hard stop. Okay. Well,
The only question I have is, can I come to work
suggest,
for you
okay.
guys?
That's,
I'm
That's
a,
what we're
like,
trying to do.
They're looking for
recruit,
interns.
yeah.
They're looking for interns.
What's that movie about the old intern
Oh,
that just
yeah.
came out?
I'm gonna Google it. Yeah.
I have a random thought.
Farrell.
Yeah.
For scalability, you said you could make it bigger, of course, but some of these are like commercial off-the-shelf parts. How could you make it smaller?
That's a good question. How small do you want to go?
You were talking about Waldos earlier, and you know, when I thought about that, I tended to think of like the really tiny micro world. But I don't know. I'm just
that's
actually,
where
that's
I'm
good.
interested in
asked that
too.
because,
So
yeah,
You mean
yeah, that was more.
nano arm?
You got
Somewhat
something
atoms and that sort of thing.
because
You can't
I
go
want
that
to
small
go
with
small.
this kind of stuff.
As big as the universe is up, it's as big.
Yeah,
down.
well, the galaxy. So I mean, you know, a lot of this was inspired by Feynman's famous paper. There's a lot of space down below. You know, the idea that the scale between human scale and the atomic scale that's the same number of order of magnitudes as it is between our scale and the size of our galaxy. Right. So there's a lot of space to go down into there, and yeah, we absolutely will. The whole control system is organized around this whole calibration motif, so that it's scale independent. And yeah, we definitely want to build teeny tiny things. But the way you build teeny tiny things is you need something that gives you the ability to assemble teeny tiny parts. And that's the fact that we can do 50 microns now, and we can do submicron, with just some minor tweaks. Then we can use this as a tool to start building things at that scale. We've also got another couple of end effectors that we've got designed. One of them is an inkjet that actually can do like thin film transistor printing, but you can also use that same technique to actually inkjet the ABS juice, and do picoliter type of dot matrix printing, and instead of thermal bonding, then you can actually do solvent bonding at that with those tiny scales and actually 3D print things at much smaller scales.
I don't want to burst your bubble, and I'll probably get kicked out of the room, but there are these little 2-micron machines that do so many different things. They're called bacteria.
Exactly. Yep. Yep. And we want to go down and help them out.
Yeah. So you were talking about having one of these assemble another one. The wiring is an interesting thing.
It is.
I'm a huge fan of the old slip wrap vector. Okay.
Yeah, absolutely.
Somebody who knows.
Yeah.
I've always wanted to see a robot do that.
That's
I think
what we
it would
want
be
to
so
do.
smart.
Yeah, that's one of the tools I told these guys about, just being able to do wire bonding, in 3D. So the whole idea of heterogeneous digital manufacturing includes this idea of printing your thin film transistors and then wiring them up in and laid down another layer of plastic and do another set and keep wiring. So you've got a 3D cube of computation and all wired together with
the heat pipes and everything built in.
with your
Other question?
manifolds or heat.
Got to pull it
Okay,
anyway.
so like, have you done any like test runs to print it?
No, actually,
Because I have an idea for a test run. Why don't you just like use a test run to your advantage and try to have it build a larger version of itself?
That's a good idea. Build a larger version too. That's something it could do. Yep, because it's an external envelope by a 3D printer.
The X or is IK? What do you got?
Yeah, we're in the process of doing the inverse kinematics so that we can actually take all CNC code and G code and stuff like that, so that we can actually inherit all of the existing 3D printer slicing stacks and stuff.
And then
So-
just shove the rasterization down onto the FPGAs.
I'm not sure I understood that.
Okay, so this right now it's polar coordinates, right? The inverse kinematic. You need to do the inverse kinematics in order to orthogonalize it so that all the existing software that's out there that thinks it's a gantry system, you can use that.
So you can get it to run G code, is basically
Get
what
it
you're
to run
talking
G code, and then we can use all the open source, 3D printing,
Slicers
slicer code and stuff like that to turn it into a 3D printer. But yeah, so that's that's actually the next few weeks that we're.
That's just a lot of really big math.
It is, yeah. And we have a big math machine.
in there.
Has anyone used IK Fast? It's an open source inverse kinematics. Okay, I'm just curious.
Yeah.
That's the one I was
Also,
looking at.
the inverse kinematics is fairly simple for this because if you turn it sideways, it looks like a SCAR robot. So you know the whole 3D, the X, Y, and Z can be solved symbolically.
Well, it strikes me you could just write a program to do it, just hard code it.
Yep.
And, well, maybe you wouldn't want to do that because your ARM design is parametric, and then you but still the program's going to be the same, right? It's just going to have different parameters to it. So
coefficients in there.
just write a program.
Yeah. Well, we've been
Hire me and I'll work on that.
All right. There it is. Kinematics.
It's a 6-month internship.
Right.
We need it done in 2.
Yeah.
Internship, that's what I meant.
I'll have to talk to my wife.
But just think how much fun you'll have.
You notice I'm not turning it down.
Yeah.
I know. I'll have to talk to my wife. I would consider it myself if I could do it. How about something scaled up to the size of something like Super Canada ARM type stuff? For
actually,
assembling remote control type
we're working
stuff.
with a builder actually.
Oh, really?
They want to take, and the thing that's really compelling to them is that the idea that you can have a small robot controlling a large robot and actually have that tactile, that haptic information.
That's what I was
there.
thinking. Yeah, so you could
pick up a 5-ton beam and it feels like a 2x4. So you can feel when it's it's in the bolts now. You can feel it click in.
And you wouldn't necessarily have to be standing under it if it falls
That's
on you,
his
but you would
biggest-
feel.
Yeah, that's the number one
That
cost
5-ton
in building
beam is a pound.
is the liability insurance.
Right.
These, people falling off roofs and stuff like that.
Right.
That's more than their labor cost.
Wow.
So it could. Well, I mean, the concept. I mean, obviously the.
Yeah, you gotta get
mechanical
pitch
aspects,
orders.
Yeah, right.
But but with this control system, it greatly simplifies
Right.
building any kind of system.
Right.
Just put some motors on there and the encoders, and the control system takes care of the rest.
Yeah. Well, I'm thinking in terms of like even assembly and really dangerous
Yep.
things like outer space.
Yep. Radiation hazards.
Yeah, cleaning up kind of radiation spills from blowing up nuclear reactors.
Yeah.
I don't know what the electronics would do in terms of the hardened, but yeah, I mean, at least you'd have the flexibility.
Yeah, actually, one of the projects we did with when I was with the other company is we did the next generation space computer, because we can do some very interesting tricks with bitstream scrubbing and stuff, and make these things rad hard so that they have much fewer failures, or they don't have failures, they're just recoverable.
When you say these things, you mean FPGAs?
Yeah, PGAs. Yeah.
I mean, is that like a level of redundancy for?
It is.
For
It's a
failure
treble
modes,
loading
or-
system, but it's also you use the silicon on sapphire stuff just for the control elements.
Just
of
like
it.
the
And then
Lotus
FPGA becomes a signal processor, and
Right.
then the signal processing, the errors just become noise in your signal processing.
That is so cool. My first microcontroller was an 1802.
Oh, really?
Yeah.
Mine too.
Oh, was it really?
Yeah.
Cosmic
the
Elf?
Cosmic VIP.
Ah,
The VIP.
it's great. So you had the VIP, I had the Elf.
Yeah, I remember the Elf.
Medtronics. Yeah.
I'm an
256 whole bytes of RAM.
Inside India.
Cool.
Incredible. So, how much are you going to be pricing this at when you get to some kind of reasonable production rate where
Yeah.
you can say,
So
hit it?
the hardware kit, if you print your own, well, from here now to the end of the year, it's $2,000, everything in the kit.
When you say everything, you're talking about all the electronics.
All the electronics,
So you
all the
3D printed-
printed parts.
Oh, that's
all the-
everything.
Everything.
Oh, that's
Yeah.
the kit for total assembly.
Total assembly.
Wow.
Now we put it together.
Yeah. And you put it together. And after the first of the year, it's the price goes up for. We will sell all the hardware except for the 3D printed parts for $2,000. And
We have a
fully
couple vendors
assembled-
that have our files already. If you don't have your own 3D printer.
Yeah,
I'm just saying.
got the
We're-
Voodoo
We built with
manufacturer.
theirs, and it's PLA. It's not ABS.
The kit is PL.
Well, no, the ones from the third-party sources.
Is
from Voodoo,
PLA.
yeah, so if you want to just order them, if you don't
Why
order
would it-
yourself,
Why
well, you can get the
order
parts from
ABS?
us in carbon, the carbon
No,
fiber
this
builds
is
stuff.
we print with
And
ABS
that's
carbon fiber,
$600.
but we wanted to make sure that our specs
$700.
be printed elsewhere. So we sent
Are
it
you
to
including
Brooklyn was Voodoo Manufacturing, which
So you're
is,
basically
it looks like
planning
it's a
on
maker
moving
bot.
out of the 3D printed
subsidiary,
stuff,
but
providing
independently owned.
electronics and
They don't
We'd
work
like
with
to,
ABS,
yeah,
so we
get
just said,
together
all right, we'll
people,
take
bring these and getting,
PLA.
the service bureaus,
I,
not the
I'll have to
expensive
check
ones,
with
but
their
things like
pricing,
3D
but
Hub and,
we just said, if you don't have a printer,
reasonable.
we trust this vendor.
Well, I think
3D
most of
Hub
these
is
are
another one we're
hobbyists
waiting for
who
pricing
definitely
back.
want to print their own.
Because that would be,
3D Hubs
Because I mean,
pricing can vary.
it doesn't look
It
like the
can.
parts are tremendously
And that's where I
difficult.
don't think, that's why we
Unless
have
you just don't have the patience.
a standardized
Yeah,
price.
it's
So
a
my goal
because-
is to
I'm
minimize
sure
any
it's
transportation to
many
it.
$100
Print it out.
Right.
You just
Depending
walk
on
down
what
the street and
assembly.
grab your parts.
It's a
That
very
way
You
complicated
should
unit to
still,
put together.
say,
We
like, use
call the
3D printer hubs, because what happens
So-
is
so
you
wait,
get
hold on.
similar spec
Okay.
from people.
So how many
Because it's about,
people
without
has
the
anyone
skin,
yet
and
3D
to me
printed
this-
one of these things
the
and assembled it
skin
and gotten
is
it working
as expensive
outside
as
of
the
the
rest
company?
of the parts we build.
So
So it's
you hire
about
the first
just
guy
the
you get?
parts. And I think it's 87, and that includes
Give me
some
your
of the tools
contacts.
we
Don't
use
look at
that
me,
don't go on the
I'm
robot,
heavily
they just help to
buried.
manufacture.
Exactly.
We're actually ready to
About
ready to
8 beds full,
and
and
advised by our
probably
legal counsel. If we
80
do that,
hours of printing.
we literally get ourselves into a lot of trouble for the future development. Because
Yeah.
there are companies out there, big companies, they do reverse engineer.
Yeah.
And
Yeah,
anything
the
they
first
change,
people-
we were lost
So
on the
then
ground.
we'll
Even our
open source
own
that
knowledge,
geometry,
we cannot work.
and then open
Yeah,
source kind
yeah,
of
Google
the
actually is the one that
interactions.
bought that out
And
of
my
the
advice
first
to just
robots.
keep your eyes
14 hours
on
they
open
bought
source with the
every
FPGA anyway,
every
and just create that,
thing we put on
would
the
be a bus for anyone else that wants to play with it or drive down. So our thinking is just a
So-
panel and type in your
So
equation code,
so we call them and tell ourselves we cannot
reconfigure
so
your
if you
chip
want, we
Please stop.
online.
Yeah.
The compile, that's the other thing is,
Wow.
Ken software, when you make a change, the
Huge.
FPGA doesn't
They're not
compile the whole
surprised when we
chip,
call
just
them.
looks
They
at what
don't
got
understand.
changed.
Fine.
So we did 3 months of new stuff.
Wow.
It
So
took
you-
22
you-
minutes
you buy the
to
$2,000
pump it all
kit.
to the
How many
other
hours
two.
of assembly do
And
you
just-
do you have a
So
sense of
it-
how
and
many
that's that
hours?
other compiler. Let us, we'll play with the FPGA, but make sure you got access to the power you want without the headaches. Because HDL and the other Verilog.
Well, I was assuming you
terrible.
buy the 3D
But
printer parts.
they're just, they don't do the deep dive.
Well, they were developed so long
So
ago.
it's,
It's a very challenging, but
Basically,
It's
you
hard to
should
change.
put aside at least
It
2
is.
weeks, probably
People
more
know it,
like
but
3 weeks or a
we're
month
still saying,
Yeah.
all right,
more like,
we want
a month
more
would
people to
fair.
have access to
with a
that.
terrace.
that's why we call it
And
DOS.
that's, we've been, we were up in San Jose 2
Well,
weeks
it's
ago,
also,
Altair asked us
making
to
this
come
into
in
something like
and sit
prosthetics.
down with
Oh, yeah.
them. And that would be great strategic partner, but they said,
They
get
say
that,
they just want to
there's
get worse
crap
and
off.
be done with it.
Off your machine, I shouldn't be talking to you.
Opportunities.
But we do have an Altair board. We're agnostic.
Yeah.
The FPGA, they were pushing for ARIA.
Well, yeah, you guys are
Okay, because then
You guys are
have the
doing
bandwidth
all this,
for
yeah.
the vision system.
This
It's
is part of the
as a
startup,
dogma.
I'm assuming,
Because
all that process,
running
is this your main job?
modules.
Everyone's.
One of those
Main job,
photon net.
and many hours a week.
So, that's with the Bill and Melinda Gates, so
Well,
take 500 frames a second.
Just get that out of the way.
One lady
Track
said,
at 4,000 mosquitoes. Measure the wind speed of them.
My
So,
problem is not only
different
am married, I have
males
kids going out
versus
to sea.
females have different wind speeds, and they're all eliminate them. Then you eliminate males, and you measure those, measuring.
Oh, well.
Sick females with malaria have a different wind speed.
No, you can be
So-
fascinated when
And
you're-
so you measure out those, and then you fire a laser at it.
So our official is time. Thank you very much,
Thank you,
team
Hansel.
Haddington
Thank you
Dynamics.
very much.
And then if you guys can stick around like next 5-10 minutes to answer questions individually, that'd be fantastic.
You guys want to?
Okay. And next week we don't have anything scheduled yet, but we might have Rational Robotics coming in. So I'll let you know through Meetup if they do come. So yeah, that's it. Thank you very much.
Thank you, Hansel.
Thanks for having us.
Thank you.
You want to see a?
Thank you guys
Single-player
for
race house?
coming out.
Can you pull up a
Yep.
website?
Yep.